thank you all for coming out to today's session. We'll be going over ArcGIS GeoEvent Server, applying real-time analytics. My name is Gregory Christakos. My colleague here joining me is Eric Ironside, and we're both product engineers on the real-time and big data team here at Esri, working specifically with GeoEvent Server. Let's go ahead and get started. Just a brief overview of today's agenda. We'll go into kind of a light glance of what it means to perform analysis in real time. We'll take a brief view at some of the components that make up a GeoEvent service, kind of at an introductory level. And then we'll dive into a couple use cases showcasing some of the new and as well as old analytic capabilities. And then we'll have some time for summary resources as well as questions at the end. So let's take a look at what it means to perform analysis in real time by reviewing several of our processors and their capabilities. But first, we're going to discuss the core capabilities of ArcGIS GeoEvent Server. So GeoEvent Server is a functional role bringing real-time GIS to the ArcGIS Enterprise. This particular product provides 5 key capabilities for your enterprise when ingesting real-time data. So the first capability is ingestion. So the ability to bring in high volume or high velocity data from connected devices, sensors, things in the Internet of Things. We might be able to, or we might be bringing in vehicle data, aircraft data, data from sensors, things of that nature. Once we bring that in, we can then do some sort of real-time analytics as our second capability.
You have to just get it closer.
Sorry, everybody. Can everybody hear me a little bit better? No? Can everybody hear me a little bit better? All right. I'll go this way. Okay. The next capability that we have is analytics. So performing some sort of real-time, or GeoFence capable of performing real-time analytics. So once we bring that data in, we might want to enrich that data, identify patterns of interest on the fly, things of that nature. Third capability is storage. So once we bring that data in and we've manipulated it or changed it in a way that's useful for our work, we might want to store that data somewhere. So GeoEvent supports storing data, whether it's in your traditional enterprise geodatabase or the spatio-temporal big data store, which is pretty unique to GeoEvent, as seen here. Sorry about that. All right. The fourth capability is visualization. So once we bring that data in again, we do our analytics. We might want to display it in a web map client or visualize it for some sort of purpose. So GeoEvent supports through a variety of different services and interactions with the rest of the ArcGIS Enterprise that visualizing component. For example, we have stream services. These are specific to GeoEvent Server, where we're not necessarily storing the data in a database, but rather using WebSockets, we're just pushing that data directly to the client. And then lastly, once we do all this ingestion, analytics, maybe storage, visualization, should we choose to do so, we can actually disseminate that information out somewhere. So maybe we want to send an email, or maybe we want to store that data in a enterprise geodatabase, so that way somebody could visualize that on a web map and react to what they're seeing in real time. And that brings up the last key point here is actuation. So, by sending emails, we might be able to get someone from an operations point of view to respond, to the information that we've processed in real time. Likewise, this could be used to interact with like the Internet of Things, where maybe we have devices on gates, for example, and we don't. It's useless to know that the gate was opened 8 hours ago. We would want to know that that gate was open now, or that door or whatever was open now, and so we can actuate by getting that information in and out in real time. And so with that, when we talk about ingesting real-time data and doing analytics on real-time data, really what we're working with within GeoEvent Server is a GeoEvent service. So a GeoEvent service pretty much configures the flow of events or GeoEvents. So as that data comes in, we might perform some sort of filtering or processing on it. and then we can output that and share our results. So just to kind of break down the anatomy of a typical GeoEvent service, in green here we have our input connector. This essentially is, what we've configured to allow us to bring our data in through a variety of different formats. You could have one or more input connectors within a GeoEvent service. In blue, we have our output connectors. These are essentially what allows us to push our data out. So where are we actually sending our data to? Are we sending an email? Are we sending it out to a stream service? Are we sending it to a map or feature service? These are some of the things that we can configure as output connectors using GeoEvent. In yellow, these yellow rectangles here, we have our processors. So this is what allows us to perform analytics in real time, and this is going to be the core of what we're going to discuss moving forward. And then lastly, we have our filters, these yellow diamonds here, and this essentially allows us to evaluate our GeoEvent based on some sort of spatial or attribute-based criteria, and either let that information pass or drop it appropriately. So now we're going to take a look at a demo, and for those of you who attended our intro session, this might look a little bit similar in theme, but this is going to be a scenario that illustrates a number of these key capabilities in action. So overall, what we see here is a couple different search areas that we're treating as geofences, and we have field crew members working in the field. As these field crew members kind of traverse the area, we're going to get updates about their location in real time. We place special emphasis on knowing when they go from one zone to another, so we have a separate set of notifications that will display showing that movement from one area to another. And likewise, we also are going to we're going to visualize a separate type of notification showing when they leave the zone altogether. So maybe that from an operations point of view, we can respond to that. So let's go ahead and take a look. So again, here we got the field crew, and they might have some sort of GPS device or something of that nature that's reporting this information to us. We're able to pull that into GeoEvent to get their location. We have a couple different filters set up to detect and create separate outputs as to when they change from one zone to another, as shown in the yellow exclamation marks, or when they leave altogether, as shown in the red. So let's take a look now at what the GeoEvent service looked like that made this all happen. So the first part we want to look at is the input side. Essentially, we're taking the simulated field crew data and we're passing that out to a stream service. This is what allows us to visualize their location in real time. And this is immensely powerful information in and of itself from an operations point of view. We have a filter in place where we're only filtering for those records or those individuals who have a attribute of search team. So we might be getting some other type of field crew data coming in, but we're not interested in that, so we can filter that out. Using the incident detector processor, we can detect when the asset or the field crew member changed zones. And then we can display that separately via its own stream service. So this is how we're able to visualize those little yellow exclamation marks when they change those zones. And then lastly, we have a separate incident detector to detect when they've left all the zones entirely. And we might have a different type of notification on the back end to actuate against this. And this is how we're able to essentially visualize these red exclamation marks showing a different type of real-time event. So now that we've reviewed the key capabilities of ArcGIS GeoEvent Server and took a brief overview of what a GeoEvent service looks like, I'm going to turn things over to my colleague Eric, who's going to go a little bit more into the components, followed by a demo.
Thank you. Thanks, Greg. Okay, so taking a bit of a deeper dive into each one of the components that we just saw, starting with filters. So filters evaluate a set of conditions that results in either a true, it passes the event on unchanged, or false, it blocks the event and doesn't allow that event to pass. A filter will never change an event, and filters can apply both attribute and spatial conditions to their evaluation. So spatial operators evaluate the event's geometry against in-memory geometries called geofences. This can be applied to all geofences, categories of geofences, or specific geofences, and we'll take a look at that in a little bit. And please note that you can even use this, you can even use event field values in the regular expression to select which geofences are operated on. Once again, we'll take a look at that in a second. So filters appear as yellow diamonds within the GeoEvent Manager user interface. Within a single filter, you can chain conditions together. You can chain them together using the and, or, and not Boolean operators on the far left-hand side. Oops. This is, okay. It's a bit tough to see here, but there's a, so the Boolean operator is over here on the left-hand side. And then the green plus at the bottom allows us to chain the conditions together, and we can even nest groups of conditions together if need be. Processors are the next component that we'll take a look at. So processors in the UI were a yellow rectangle. Processors manipulate an event's data to produce a modified result. So there's many out-of-the-box processors, and they all allow you to manipulate the attributes, the schema, and/or geometry associated with an event's record. In addition to the processors supported directly by GeoEvent, several other processors have been developed for specific use cases and are available on the gallery. At 10.7, we're proud to offer the additional set of processors based on items previously released in the gallery. These include the ones at the very bottom here. So we've got add XY fields, range fan calculator, bearing calculator, event joiner, feature to point, event volume controller. And we're going to try to show as many of these as we can in our demonstrations later on. You can create custom processors yourself using the SDK. And also other people have created processors and released them as well on GitHub. So I encourage you to search the community to see if you can find something that you need. Okay, when it comes to processors, some processors work only on the geometry and event. So the buffer creator, the intersector, or the projector are examples of these. So they're going to take the geometry and do something with that geometry. Other processors work with the fields of an event, so the field calculator, the field enricher, field mappers, stuff like that. And then the final set of processors are going to look at the conditions associated with an event as it's going through. So event joiner, the incident detector, track gap detector, these typically are looking at the data that's got some sort of a statefulness to it, and they look for the conditions to change. So entering a geofence or exiting a location or something like that. The role of a processor is to make some modification to an event and send it on, or detect some condition and generate a new event record. In either case, a processor promotes events that have been modified in some way. So a quick note about spatial operators. These spatial operators appear in both filters and processors, and there's two things going on within a spatial operator. The first part is the any and the all here. So these apply to the group of geofences that are operated against. So any operator will look at any geofence. It doesn't have to be all of them, but so long as one geofence satisfies the condition, then the filter or the spatial operator is going to pass that event. And the all is kind of an and, so it's going to require that all of the geofences in that group have that same condition to apply before it passes the event on. The regular expression at the end here allows you to filter the set of geofences that this spatial operation applies to. So you might be looking for safety zones or hazard zones or asset locations. So you can use that to kind of specify what the filter or the processor is looking for when it performs its spatial operation. So, for example, looking at the any here, the first one on the top left is going to intersect the incoming event geometry with any geofence in the system. And so long as you get one intersection, then that spatial operator will evaluate to true. On the second one, though, on the right-hand side here, we've limited the number of geofences to be just hazard zones. So we're looking for an intersection with any hazard zone, and if that is present, then we would pass the event on through. If it's not intersecting any one single hazard zone, then the event would be blocked. Looking at the first one here is going to be looking at the event's geometry being inside or disjoint from all geofences. So let's say you had a set of safety zones that a user had to be within, and you're looking for them to be outside of all of those safety zones. The second one, or I guess the first one, the regular expression was not set, so it would be any geofence there. The second one here is looking for the disjoint of all safety zones. So if your operator has gone outside of the safe areas within your plant or something like that, then you can alert on that and start to send an email or a text message. Using some pictures to kind of look through the same thing. So the one on the left here is going to work through the any. So assuming that the dots going through are like a user or a vehicle driving through a system, if we use the any operator, then the yellow dots here are the dots that would pass through the spatial filter. So these are located within any one of the or more of the geofences. Looking at the all, you'll notice that the yellow dot is now confined to the single dot in the middle, which is inside of all geofences. So looking at the spatial operators that we have both stateless and stateful operators. So stateless are going to be things like inside, disjoint, outside, touches. So they're things that can be evaluated instantly given the two geometries. Stateful are going to be looking at changes in the state of the geometry. So they need to maintain some sort of a cache of the event's location. So they're going to look for situations where the event's geometry went from outside of a geofence to inside for entering, or vice versa for an exiting. Geofences can also be, just a note, geofences can also be lines, points, polygons. So it doesn't necessarily matter what kind of geometry you have for a geofence. And all of the spatial operators should support a variety of different geometries. So check the documentation on your spatial operator, but for the most part, they should be supporting all of the different geometries that are available. So I've mentioned geofences quite a bit up to now, but I haven't really showed you how they are created or managed. Geofences are geometries that are stored in memory. So they're typically read from a variety of different sources. And they're stored using a category and a name. So the category is, like I said, hazard zone, safety zone, asset area, property, parcel value, or something like that. And then the name is going to be unique. So you have to make sure when you pull your geofences in that the name of each geofence is unique. We also keep in mind that since they are stored in memory, there may be limitations on how many geofences you can store in your specific GeoEvent server. So it depends on the geometry complexity. So think of points versus very complex polygons. There's going to be a difference there in how many geofences you can store in memory between those two. GeoFences can be loaded into GeoEvent using either feature services or stream services. And you can use a one-time import. So as you see here, you would connect to a feature service and load the contents of that feature service in and then be done with it. So this might be like state boundaries or county boundaries, things that don't ever change. The other option would be to use a synchronization rule. So synchronization will periodically go and refresh the geofences. If you consider geofences that are moving, like boundaries around assets that are moving, or maybe your property boundaries change or your plant boundaries change quite frequently, then you can read those in on a frequent basis. You can read these in from one of two sources, either a feature service or a stream service. When you're looking at synchronization for geofences, there's a couple more options related to the life cycle of these geofences. So they do offer you the ability to set a start and an end date for when they're active. And you can also set an additional parameter for whether they are active or not. So it's a yes-no parameter of whether that geofence is active. And all of those are synchronized from the underlying feature service, so you can have other GeoEvent services changing those as need be. So you may be wondering why we need a geofence to be updated. Dynamic geofences can be really powerful. They allow you to evaluate spatial relationships between different real-time feeds. So consider, for example, two independent real-time data feeds. One provides a location with an implied area of effect, and the other provides the current location of commercial flights. So every time we receive a new location from the first data feed, the red dot, we use the GeoEvent server to compute a buffer and broadcast that buffered area via the stream service, and we update the geofence. By making our geofences dynamic, we can detect and notify in real time when a commercial flight's position intersects an area buffer around a moving point. And if you're thinking the big red circle has to be the geofence, think again. So the flight itself, the points could have been the geofence, and the moving circle could have been the events going through the system. Which brings us to the first demo. So in this case, we're going to try to identify some unsafe conditions in our work area. So to set the stage for this demo, we're interested in monitoring the safety of various assets in our system. These assets can be fixed, such as offices, exposed, such as construction sites or plants, or mobile field crews. For this scenario, we are constantly updating the vehicle location of field crews so that we know where they are at all times. The hazard we are monitoring is lightning within an operational area. Finally, we are monitoring for lightning strikes that are near our assets, both fixed and mobile. If we detect a lightning strike within a specific distance of an asset, we want to notify them in the best possible manner. So for plants or offices, this is going to be an email blast alerting all of the staff to find a safe place. And for field crews, it's going to be a text message and an email to the field crew boss and his manager that they should return to a safe zone until further notice. So when a field crew receives a notice for this scenario, it is expected that they will immediately pack up and return to the closest plant or office. So I'm going to go ahead and start the demo. So the yellow dots coming in with the red circles around them are the lightning strikes. You can see we've already gotten one notification at plant 2 that they need to take cover. And there's a field crew 1 out there, and they've just been notified via text message that they need to pack up and come home. And so we see that they start to progress here. And as the field crew progresses outside of the red zone, their status is cleared, but they're still required to come back to plant 2. So they're going to head back to plant 2 here. And after a while, all of the incidents clear, and the field crew makes it back to safety. So looking at the service, the GeoEvent service behind this demonstration, it monitors the locations of the vehicles and is constantly updating where our mobile assets are. So the only processor in this case is a field mapper used to translate the schema of the incoming data to the outgoing schema. Field mapper is one of the most important processors you're going to use. It probably should be used in just about every service that you have, especially in your outputs, in order to make sure that the that the data is in the right format. So the field mapper itself can change schema or structure of an event record. So we can reduce or add fields. We can change the name of fields. So if you look on the left here, we have a relatively complex structure, and we're just going to map over a couple of the different AVL type fields from that data feed. So we know the velocity, heading, and location of the field crew. The second GeoEvent service operated on the Lightning. So this service was typical of the ones that I've shown so far. It's got an input, it's got processors, field mapper processors, and outputs. So the top part here is used to create the points of lightning on the map. So these created the yellow points in the middle. The second part along the vertical here is used to create the buffers around these points to serve as hazard zones. So the first processor that we have here is going to calculate the distance for the buffer zone. The next thing we do is do a projection, and then we buffer that. So we have to project into a projected space in order to get the right kind of zone around that. So looking at the buffer creator, we're taking the point geometry in this case, applying a 5-mile radius around it, and generating that buffer and changing it to a polygon. So the output of the buffer operator is always going to be a polygon of a certain distance bigger than what it started out as. The third GeoEvent service used in this demonstration compares the current asset locations with the lightning strike hazard areas, which were the buffered red polygons. To do this comparison, it uses an incident detector, which waits until an asset is detected inside of a hazard area before triggering. Once triggered, the incident event is joined to the original event that caused the trigger, and the joined event is passed through. From here, the joined event goes directly to the feature service. It is also used to create either an email or a text message based on status and target of the message. So taking a look at the incident detector itself, we're looking to detect a condition that has occurred and monitor the duration of that incident. It starts with, oops, let me go back here real quick. So it starts with opening conditions and optionally closing conditions. So the conditions here could be the spatial operator entering, exiting, or it could be some other just textual feature attribute of the item, such as speeding above 80 miles per hour or something like this. In our case, the field crew was detected within, or an asset was detected within that 5-mile radius of the lightning strike. When the opening condition is met, this opens the incident, and so long as the opening condition continues to be met, or the closing condition is not met, then the incident stays in an open state. Once the closing condition is met, then the incident transitions to a closed or ended state. Looking at this a little closer and graphically, so the opening condition for this incident detector is set to monitor the asset and a geofence category lightning. So the first two messages for the track ID appear without any incidents because they're not inside of the polygon here or the hazard area. When the track ID is detected inside the named geofence, an incident is generated. The status of the incident is started. Let me go back. So the status of that incident is started, and the duration attribute indicates how long the incident has lasted. So as more events come through, that vehicle seems to have stalled or has stopped within the hazard area. You can see that the status continues to be ongoing, and the duration continues to update. And then once the event moves out of the hazard area here, you can see that the incident ends, and the duration is fixed at its final value. The status is updated, and there's no more updates on that incident. as events continue to flow through the system. So in that case, once an incident has been detected and has been passed out of this top right processor, we've got an incident, but we don't. The incident schema has changed, so it's now an incident rather than the original vehicle field crew information that we had. So we're going to join that information back to the original data in the original event. So we use an event joiner. This is a new processor at 10.7. And let's take a closer look at the event joiner. So an event joiner will cache events from two different GeoEvent definitions, and it's going to join them when it has one event from both definitions with a matching key value. So the key value can be anything that you choose. This is useful for bringing together two separate events that may apply to the same thing. In our example, we're getting one stream of events with a location, another stream with a battery level. If two events apply to the same vehicle, they are joined and sent on their way. So here's our two events coming in. And the track ID here is going to match for both of these. And so we end up with a matched joined event going out. And so the two incoming event definitions must be two separate event definitions. So you can't use the same definition coming in, or we'll never know when it's got two that match. However, the field names in the outgoing event are renamed to include the incoming events definition, so you can have matching fields between the two event schemas. And you can see that here in the picture with the A underscore and the B underscore naming the field events, or the events field, the event fields. So all three from the event A came through, and all three from the event B came through. And they match on the track ID. So that was the key used in this case to join these two. The event joiner has a couple of other options. So the first is a caching option. So of the caching option, there's two modes that you can set that to. So the first is a clear mode. So every time the event joiner receives exactly two new events, it will result in a joined event, and then the cache will be cleared. So you can see we get event A and event B. They get matched and sent through, and the cache is now cleared, which is represented by the two empty squares in the green box there. The second option is to set it to don't clear, which means that it continuously caches each event type, and it will use the last known event. So if we get event B in here, and then we get event A, that makes one join. If we get a second event B, it's already got an A in its cache, so it continues to join those. So this might be useful for situations where you have events coming in at different speeds. So for example, if you have an event registration that has like license number, VIN, and the driver that's supposed to be assigned to that vehicle, and then you're getting AVL positions every 30 seconds with just the GPS location, heading, and speed, you could use those two to join up events and show that driver A is where driver A is at all times. So that concludes our first demonstration. I'm going to have to hand it off to Gregory to do the second demo.
Thanks, Eric. All right, so we're going to take a look at a second demo here. This one, we're calling it Tracking and Asset Recovery. It's going to showcase some of the new processors. So this demo is going to showcase a scenario involving kind of the real-time tracking and recovery of an asset in a field by a crew of 3 individuals. In this case, they're tracking some sort of large mammal out in the field. The data coming in from the mammal feed as well as the tracker feed, 2 different inputs, they're going to be at different rates, but we can still perform some useful analytics on that, even though one might not be near real time, whereas the other is. So let's go ahead and take a look at this. So represented as blue points, we have our 3 trackers moving along the road. And again, they're seeking out a large mammal that was reported in the area. In red, we see that the GeoEvent service has just received the last known location of that mammal. Now, because the GeoEvent service has obtained the location of each feature, It's immediately able to join these records using the event joiner to establish, using both the geometries of these features, a dynamic bearing and range fan in real time. The range fan gives us tremendous insight from an operations point of view, since we can essentially get an idea of what these people might be seeing on the ground, especially as they traverse through the open areas as well as the wooded areas. Now, as our GeoEvent service continues to receive the last known location of the tagged mammal, we can see our trackers adjust course using the bearing that's provided to them. And then each range fan gets updated as well. Now, as the tracker range fan crosses paths with the mammal here, we can assume that there is some sort of interaction. We have a notification display, warning, mammal encountered. And while we didn't show this in the demo here, we might send out an email at this point or a text to someone who can then respond and follow up on that event. I should say that while this scenario involved a group of trackers moving on a mammal of some sort, this type of scenario could be applied to maybe some sort of law enforcement training or red force versus blue force sort of scenario. So possibilities are kind of endless there. So let's now shift gears here and take a look at the GeoEvent service that made this possible. So to kind of begin here, similar story as previously, we're essentially pulling in the simulated tracker data, or this could be, live data from out in the field, and we're essentially pushing that to a stream service to show the location of these trackers in real time. That's what gives us these little blue points as they move around. As we get the updated location, we can then display that. You might notice below that, the same thing is happening with the mammal, even though I don't have it highlighted here. Essentially, we're pulling in that data, albeit at a slower rate, and we're displaying that in the web map. That's what gives us the red point showing the mammal. Kind of moving on to the real meat of this GeoEvent service, though, we have our new processors here. So once GeoEvent has received the location or the data related to each of the trackers, and has also received the data or the location of the mammal, we can pass those records to the event joiner processor to essentially join those records together since they share a common value. And then we have both those geometries in the same data set as one record. And then using that combined record, we could then pass that along to the bearing calculator, where we can treat the tracker as maybe our origin and the mammal as our destination, and establish that dynamic bearing between those two features. So when we think of bearing, oftentimes we're thinking of, a moving feature as it's trying to get to some fixed object, but that might not always be the case. You might have two moving features, and you want to establish a bearing between those. We do a little bit of schema correction using the field mapper. It's not so important for right now, but once we have all this data together, meaning we have all the tracker data, the mammal data, their geometries, the dynamic bearing, we can then pass that to the range fan calculator, where we use bearing as well as a range value and an arc angle value to create those dynamic range fans. And then we ultimately are pushing those range fans out as their own separate stream service. And that's how we're able to visualize these range fans in real time. Additionally, once we get that range fan, we're passing that to the incident detector to essentially look for when does the incident detector intersect with the mammal. And once that happens, that's when we can send out a separate notification via its own stream service. And that's how we get these little red exclamation marks here. And lastly, while this wasn't shown in the demo, we have the event volume controller to essentially throttle the rate of messages that are sent. So this is important because if we're looking for when the tracker range fan intersects with the mammal, and that might be updating every 5 seconds, we don't necessarily want an email sent every 5 seconds to a manager saying, hey, there's been an interaction, hey, there's been an interaction. So we can use the event volume controller, which is another new processor at 10.7, to throttle the rate of those messages being sent. So now we'll take a closer look at some of these new processors, starting with the bearing calculator here. So the bearing calculator, you want to use the bearing calculator when you want to calculate the bearing, as implied by the name, or heading between two sets of points or two sets of geometries within a single event record. So when configuring this processor, you could either specify two geometry fields or separate fields containing separate X and Y coordinates indicative of an origin and location. Using the bearing calculator, we can then return that bearing value in degrees, And we can either maintain the point geometry of the incoming record or replace it with the bearing line, essentially the line that we would draw between the origin and destination. And so in this example here, we see that we have a record. It's got an X field and a Y field. That might be our origin, and an X2 and a Y2 field. That might be our destination. Or if we're to take a look at this within the context of the demo, the X and Y might be our tracker's location at any given moment in time, and the X2 and Y2 might be our location of the mammal. Once we pass those values into the bearing calculator, we can see that we're returned that bearing value in degrees in red. Next, let's take a look at the range fan calculator. This is another new processor that's available at 10.7. So you'll want to use the range fan calculator when you want to construct a polygon, maybe representing the visual range or some other type of range forward of an event's point geometry. So this could, again, represent like a visual or contextual range of something ahead of that point. So in this case, we were looking at what might the trackers be seeing on the ground, whereas we could also apply this maybe to a vehicle to see what is that field of vision of that vehicle as it drives down the road, just as another example. So in order to configure the range fan calculator, we have to provide 3 key values: a range, a bearing, and an arc angle value. So I can try to show this here. Range is essentially the distance that the resulting range fan is going to be. So if we're thinking of this in terms of visual aspects, let's say I can only see up to 2 miles in front of me. So I might specify that within the range fan calculator as the range, 2 miles. Likewise, it requires a bearing. So the bearing is what essentially is giving the range fan its direction. In the case of the demo, we were obtaining that from the bearing calculator, and that's what gave us the ability to dynamically change the direction that the range fan was facing. And then lastly, we need an arc angle value. This is essentially what provides the range fan its shape. So think of it as like the outer degree value of a circle. In this case, we provided a range of 100, a bearing of 90 degrees, and an arc angle value of 90 degrees. Once we pass that through, we get that feature on the right there, kind of a right angle range fan. I should mention that we can provide these values within the processor as a constant. So if you always know your range is going to be 2 miles, we can put that in the processor, or we can have it look at a particular field within our incoming data. And so that way we get kind of that dynamic change. So as the data is coming in, your range is changing, bearing changing, arc angle values changing, we can see our range fans change. So constant or dynamic. Lastly, I'd like to spend some time taking a look at the event volume controller. This is another one we're excited to introduce at 10.7. So the event volume controller is a processor that you'd want to use when you want to control the rate of event records being sent outbound based on some sort of unique identifier. So it uses, in this case, the track ID tag. For those of you familiar with GeoEvent, it uses a track ID tag in order to monitor for unique events. So it requires 2 primary properties. The first is how many records do we want to let through at any given period of time? And then as implied, we want to set what is that iterating time value. So in the case of this image here, we got an event record and it has a unique track ID of ABC. And it's coming in at time 1, time 2, time 3, or second 1, second 2, second 3. And we've configured the event volume controller to only allow 1 unique event of any given track ID every 3 seconds. So this ABC record that's coming in once every second, that first record is going to be passed because it meets that condition of only 1 event every 3 seconds. Whereas the same record that comes through at time 2 and time 3, that gets discarded because, again, we're only allowing 1 event in every 3 seconds. At the next 3-second interval, it's going to pass whatever it gets first. And that's, again, what we see here. We got track ID S4782. It's unique. It's come in at time 8:05:01. Again, the same record's coming in at 8:05:02 and then at 8:05:03. The only one that's going to be passed through is the first one until that 3-second interval is up. So those are some of the new processors that are going to be available at 10.7. Let's go ahead and take a look at the summary here as well as some resources. So In summary, ArcGIS is a dynamic platform that enables continuous analytics of real-time data and visualization for better understanding of our world. And GeoEvent Server allows you to bring in this data to know what is happening as it happens. And then by getting that real-time information, we can react and make better decisions and also be notified when interesting events occur. Here's some resources. We definitely recommend checking them out. We got step-by-step tutorials at this link here. Introduction tutorial split into 6 modules. It goes into depth about pretty much all you need to know for getting started with GeoEvent. We have some other tutorials as well that go into more specific topics. We also invite you to participate on GeoNet. Got a pretty active community there. We frequently visit that to answer questions. And then later on, you might be able to get the video recordings of this technical workshop at the link below. So this was the Applying Real-Time Analytics session. Tomorrow we've got our best practices session, which kind of goes into detail of like the tips and tricks of GeoEvent, the do's and don'ts, how to maximize your performance, those sort of things. We also have a session on utilizing the GeoEvent SDK to create some custom processors, custom inputs, outputs, things of those sorts. And then Thursday we have our Road Ahead session. So please take our survey on the app. We're always looking for feedback about our sessions to see whether or not this was useful for you, how we can improve, do things a little better. So we definitely hope that you fill that out. And we'll go ahead and open this up for questions or feedback. Any questions? Yes. So the question was, isn't the incident detector supposed to do a lot of kind of what the event volume controller does? Is that? Yeah, so I've used to kind of answer that question, I've used the incident detector before in a manner similar to the event volume controller. So the incident detector, for those who might not be aware, has its own fixed definition. There's one field value of the started, ongoing, stopped. We could potentially limit the rate of a message coming through by filtering on when that field is set to started. So that way we're discarding everything else. So in that capacity, the incident detector can be used in a similar fashion to the event volume controller. I think where the event volume controller really shines is when we're working with spatial filtering. Maybe we're not actually doing any sort of incident detection, but rather we're looking at spatial filtering. So like, again, going back to my example, like when the truck enters the geofence or the facility, for example, we can use the incident detector to send a message when that starts and then block everything else via filter from whatever else coming in. The problem with that is that incident might persist and go on. And so if that truck were to exit and then come back in, you might run into a scenario where it doesn't pick up on that started again. The event volume controller is primarily useful for like messaging purposes on the outbound. So I'm not sure if that exactly answers your question. A little bit. There is a little bit of overlap depending on how you're doing filtering after using the incident detector. As I mentioned, like there's that one status field for started.
The event volume controller can also be used for high velocity events or streams where you need to look at reducing the number of events that you're getting. So for example, if you're getting something at 1,000 events per second, but you really only want to evaluate it every 30 events per second, then you can use the event volume controller to really reduce the load on your GeoEvent system. And kind of reduce the amount of events that you have to evaluate. So that's another use case for the event volume controller where you're getting data. I mean, so a lot of times you can't control the rate at which you're getting the data. And most of the time it's not fast enough, but sometimes it is too fast and we need to kind of limit or reduce that down to something that's more reasonable for what we want to do.
Yes. With the event volume controller. So the question is, do the events that kind of don't meet that time condition, do they get dropped? The answer to that is yes, which is why we recommend using it at the end of your GeoEvent service, and we also recommend primarily using it for messaging purposes. Any other questions? Oh, yes. I'm sorry, could you repeat that a little louder?
So the question is, using the bearing calculator, can you use a previous value of an asset or a track ID to calculate the bearing for, say, something that's moved? And the answer to that is yes, you can. So in order to make that happen, what you would do is, let's just call this thing a moose here. So if you get the moose track in now, you would go in and look for what was the previous location for that radio collar, and bring that in as a second geometry field within your event, and then use those two to calculate the range and the bearing for the amount that he's moved since the last time that he last reported. Does that make sense? So you would use something like a field enricher. So the event going through, you would field calculate the current geometry to like a new geometry, and store that off later on, and then you would bring in the old geometry and use the old geometry and the current geometry to do your range bearing. And then on the way out, you would do your monkey business where you kind of store off which geometry is which.
Or in the case of the event joiner with the demo, what was going on is that moose data was coming in every 5 seconds, whereas our other feed was every second. So if you have those as separate records, you could potentially join them and get those geometries together in one single record now, whereas we haven't been able to do that before 10.7. And then with that, calculate the bearing, as was done in the demo. So, yes. So the question is the range fan, can there be multiple range fans, or is it limited to just one? In terms of a single instance of the range fan calculator, it's calculating one range fan. That being said, within your GeoEvent service design, you might configure separate range fan processors within the service to indicate different types of range fans, maybe correlated to some sort of severity.
Just to expand on that a little bit, if you had, say you're calculating 3 different range fans for 3 different reasons, you could definitely calculate all 3 of those using 3 separate range fans into 3 separate geometry fields. And then on the output side, you'd have to write those out to 3 separate outputs, each one taking one of these separate geometry fields, because you can't, in a feature class, you can't have more than one geometry column. Does that make sense? Yeah.
Any other questions? Yes. And so the question. Oh, sorry. Go ahead.
No, I'm trying to make the puzzle clear. Two that kind of threw me off. There's using inside and outside versus enter and exit. Like there's very similar.
Certainly. So kind of the general question was, what's the difference between stateful, non-stateful? What's the benefit between each? You brought up a couple different examples there, inside versus outside versus, and then compare it to enter and exit. Enter and exit would be stateful. Inside, outside is stateless. So a point can be inside a geofence. If we're doing some sort of spatial filtering, we don't need to know the previous location of where that point was in order for it to be inside. let's say at the first pole of our record, that point is already inside the geofence. That's fine. Enter and exit it's stateful insofar as a point can't enter a geofence unless the location of that point was known to first be outside that geofence. So it really depends on what your use case is and like how you're tracking these features and what you kind of are expecting or maybe not expecting them to do. It really just depends on the use case.
Yeah, so just expand on that one key point here. So if you're thinking about the output of the incident detector for an inside, so if you had just it set to be while the point is inside, then you would get events out of that incident detector where let me say that a different way. The incident detector allows you to keep track of all of the geometries that were part of that incident. So you could draw a line of that event, of that item moving through the inside of that geofence. For the inside, that resulting geometry would start inside the geofence and it would end inside the geofence. For the enter and exit situation, that geometry would start outside of the geofence at the last point it was at just before it entered, and it would end outside the geofence at the last point, or the first point outside. The duration of the incident is also tracked for the inside situation. It's going to start at the first point, the timestamp of the point that's inside that geofence. Whereas for the enter and exit, the duration is going to start at the point where it was just outside, and it's going to end at the point where it's just outside once again. So the situation is a little bit different for each one. For the most part, I would encourage you to try to use stateless versus stateful, and the impact is somewhat minimal as far as the stateful requires that GeoEvent's maintaining a cache of previous positions for each one of the track IDs. And having to do that and then check that cache takes some time and some memory. It's typically not a huge amount, but it's still some. So if you can get away with using stateless conditions, it's going to give you a tiny bit better performance.
Any other questions? No? Oh, yes, sir.
So the question is, can GeoEvent calculate the speed of an event? So based on a previous position and the current position, can it track that motion? The answer is right now, no, we cannot do that using an out-of-the-box processor. However, there is a processor out on the gallery that's available. It's called the motion calculator. And what it does is it caches every single track ID going through, and it calculates the average speed, the average distance, and all of the information related to the differences between the two geometries on those events.
Any other questions? No? Well, if you do happen to have any questions, our team will be at the social. We're happy to talk, all things real time with you. But thank you all for your time. Appreciate it.